Hello everyone, my name is Zerui. I'm really excited to be here to present our work, Characterization of Large Language Model in Development in the Data Center. This is a joint work with Qinghao, Zhisheng, and our colleagues from Shanghai AI Lab, Nanyang Technological University, Peking University, and Shanghai Jiao University, and SenseTime. Let me begin with some background. Large language models have gained immense popularity due to their extensive performance and accuracy in various tasks such as brainstorming, coding, planning, and writing. However, developing LLMs from scratch requires massive computational resources and can spend several months. For example, Meta's Llama 2 model family with up to 17 billion parameters was developed using 16,000 of NVIDIA A100 GPUs over several months. On the other hand, Google AI's Palm model underwent 2 months of pre-training on 6,144 TPU V4 chips. Despite LLM's huge potential, the system-level challenges in efficiently developing and training these models in the data center remains underexplored and not well understood. The motivation of this work is to bridge the gap. We want to figure out several questions. First, what are the characteristics of workloads during the development of LLMs? What are the new data center requirements for running LLMs compared to previous DR workloads? How to tailor system softwares for LLMs, such as scheduling system, fault-tolerant system, and pre-training frameworks. First, we look at an overview of the LLM development pipeline. It usually includes 5 stages. First is data preparation, and then pre-training, and alignment, or SFT, and evaluation, and finally deployment, or model serving. In this work, we mainly focus on the first 4 stages. Development or model serving is not included in our work. To facilitate our research, Shanghai AI Laboratory built a GPU data center, Acme. There are 2 clusters dedicated to LLM development, Zerui and Carlos, containing over 4,000 of A100 GPUs in total. And GPUs are interconnected by NVLink and InfiniBand. The main difference of Zerui and Carlos shown in the table is their host memory size as well as the network configuration. While Carlos are equipped with more InfiniBand NICs. Leveraging several at Carlos, we have developed a collection of LLMs ranging from 7 billion to 123 billion parameters, which is the intern LLM model family. Our models are now available on Hugging Face and GitHub. In this work, we collect the trees from March to August in the last year. It spans 6 months, and there are over 1 million jobs. Among the jobs, 60% of GPU jobs are GPU jobs, and the others are CPU jobs. The data sources of our trees consist of job metadata, which is detailed information of each job, such as execution time, hardware monitoring data, and runtime logs and profiling data. Acme is dedicated to LLM workloads compared to the other traces, including Halos from SenseTime, Pi from Alibaba, and Philly from Microsoft. They cover general DL workloads or deep learning workloads, and Acme enjoys more advanced hardware. First is the data center characterization of Acme. We perform a thorough analysis of the workloads in data center. We first compare the workload distribution between LLMs and previous DR workloads. Contrary to the stereotype that LLM-related jobs are typically long-running, we find that workloads in Acme, which is the first red bar in the figure, exhibits shorter average GPU job durations compared to the DR workload observed in the previous job traces. It is nearly 13 times shorter than Microsoft Philly data center. We summarize some potential factors of this observation. First, Acme uses more advanced hardwares, and users tend to request abundant resources than they actually used, which significantly accelerates training process. Besides, LLM development pipeline involves numerous small-scale associated jobs such as evaluation. Besides, we also present cluster-wide GPU utilization distribution of the 4 clusters. It is evident that in the figure, the GPU utilization in our 2 clusters, Zerui and Carlos, exhibits a polarized pattern. This means LLM workloads are either entirely idle or fully active. When comparing the median GPU utilization, Zerui and Carlos exhibit significantly higher value at 97% and 99%, in contrast to 48% and 4% observed in Philly and Pi. This parallelization mainly stems from the fact that the workload in our cluster shares similar transformer-based model architecture, which are computationally intensive. Besides, many jobs fail at installation without even using any GPU. The key insight here is that GPU sharing techniques may not be optimal for LLM development. Furthermore, to study the workload distribution, we draw the CDF of number of GPUs a job requests in relation to the number of jobs and GPU time in all the 4 clusters. Our data reveals a high-screw workload distribution. From figure A, we can see that in all the 4 clusters, the majority of jobs only use 1 GPU. However, in our cluster, large-scale jobs consume large amount of GPU time, which is shown in figure B. In colors, which is the orange line, the job using more than 256 GPUs only account for 50% of total jobs, but they used almost 96% of the total GPU time. On the other hand, in colors, it shows the same distribution. In contrast, in pi, those single GPU jobs use approximately 60% of total GPU time. This scroll workload distribution in LLM development implies that when designing optimizations for ML cluster schedulers, this feature should be considered. Regarding the infrastructure utilization of LLMs, we plot the distribution of GPU metrics and memory footprint. A notable pattern is that GPU utilization in LLM development is much higher in prior deep learning workloads. Specifically, in figure A, we can see that the median SM activity stands at about 40% in both Carlos and Seren clusters, double of that of pi. Moreover, the median GPU memory consumption of Carlos exceeds 75%. However, in pi, GPU memory of a large portion of jobs are underutilized, primarily less than 25%. Now let's move on to the workload profiling. We delve into analysis of the system performance and resource usage of both pre-training and evaluation tasks within our cluster. For pre-training, we profile the pre-training of an early version of internal IM with 123 billion parameters. Leveraging 2040 8100 GPUs, we use InterEvo as the training framework. InterEvo is the distributed training system we developed to enhance training efficiency. For profiling, we employ 2 main strategies. First is InterEvo V1, the initial version of InterEvo uses 3D parallelism like a Megatron LLM with pipeline and sensor parallel size set to 4 and 8, and the InterEvo V2 utilizes hierarchical 0 for memory optimization with parameter sharding within 64 GPU subgroups and recomputing. We collect GPU DCGM metrics every millisecond and record detailed memory snapshot. This figure illustrates the GPU SM utilization over time. Figure A is a result of InterEvo V1 and the other is V2. It is evident that InterEvo V2 presents a superior peak SM utilization and it exhibits reduced idle periods compared to InterEvo V1, achieving around 16% acceleration. InterEvo V2 ensures our GPU deliver top performance in our large-scale language model training. The optimization underneath these improvements are the improved communication and computation overlap and an effective hybrid parallelism strategy. And more details of this framework, please refer to our InterEvo paper. We also record the memory consumption of each pipeline rank when using InterEvo V1 and F1B pipeline scheduling strategy. In this figure, the memory in each rank is primarily divided into 2 parts. The red part is activation, and the blue part includes parameters, gradients, and optimization states. It shows an imbalance in activation size across different pipeline ranks. As you can see, rank 0 has a significantly higher memory consumption, mainly due to activation size, which is the red part. And this imbalance results in suboptimal training performance. The key insight here from this analysis is the necessity for a specialized partitioning mechanism. Such a mechanism would not only optimize memory usage, but also improve the overall training efficiency. And our team have developed this optimization to address this issue, which have been implemented in intern Evo v2. Further detail also please refer to our intern Evo paper. Regarding evaluation workloads, we observed a high GPU idle rate causing huge overhead. The first is model loading and data processing overhead. The second is metric computing overhead, which may take up to 30 minutes GPU idle. For example, human Evo task has a data set for evaluating model coding capacity. When evaluating the model on this task, we need to actually run and test the code LLM generate, during which GPU just remain idle. For example, in this figure, we show 7 billion model evaluation on human Evo dataset as an example. As shown in the figure below, about 13% of the job duration is spent on model loading and data processing, and 19% on the right is spent on code text. Finally, due to this job, GPU remains idle for almost half of the time. The key insight here from this analysis is the need for optimization of our evaluation process in the system level. By addressing the high GPU idle rate, we can potentially improve the efficiency and effectiveness of our whole data center. Next, we will cover the failure analysis. We perform a comprehensive and in-depth study on the failure happens during the LLM development in our data center. LLM jobs often subject to early termination due to various failures. The failure recovery process typically includes several key stages for mitigating this issue. First, the system frequently saves checkpoints as the training progress at a fixed interval by creating checkpoints. This allows the job to be resumed from the last saved point. Then, a failure may occur, which can happen for myriad reasons like hardware issues or software glitches. The job just crashes. Following this, the operators or engineers of us identify and solve the root cause of the problem. Finally, the job is resumed from the most recent checkpoint. This is a quite widely used strategy. However, it still introduces considerable GPU wastage and loss of training progress. In the checkpointing process, training gets stuck when saving the model states, which is shown in the figure as a purple trunk. In the troubleshooting stage, reaction of engineers usually has a delay, and the troubleshooting itself takes lots of time. The resume also introduces a loss of training progress. The red X in the figure is between the last checkpoint and the failure point. All the computations in this part are essentially lost. To minimize the failure recovery overhead, we build a fault-tolerant system leveraging several techniques, which will be shown in the following slides. One of the challenges of building this system is that failures may happen across the stacks, from user code to pre-training and evaluation frameworks and infrastructure issues. We conduct a thorough analysis of these job failures in our cluster. Our finding indicates that the most severe failures are those of infrastructure, with NVLinks errors and other GPU errors are the most frequent, causing significant GPU wastage on time. Framework and the script errors like a session error or type errors cause less wastage, but happens the most. This highlights the areas for improvement. Let's turn our attention to system for LLMs. The insights aforementioned guide us towards building the system for development, including fault-tolerant system for pre-training and timely feedback for evaluation. We implemented a synchronized checkpointing. This technique involves two stages. First, we store the model states in host memory, and then a background process saves them to the storage. Local storage or remote storage is okay synchronously. In the figure shows the training progress of two early versions of our intern LLMs. One is 100 billion and the other is 123 billion. The method accelerates the checkpoint by 58 times from the green lines to the blue lines. Our second technique is the LLM-assisted diagnose and recovery system, where we employ two LLM agents to compress real-time logs and diagnose the root cause of the failures. This system automatically do troubleshooting and perform failure recovery so as to reduce the downtime, or also with a fallback to manual recovery if necessary. In evaluation, we develop a trail coordinator to harmonize the operations of the cluster scheduler and the LLM framework. This design incorporates the following three key techniques. First, for evaluation on the same models, models are downloaded only once to the memory and loaded directly through PCIe in each worker, significantly reducing I/O wait times. Second, we decouple metric computation. They are now conducted synchronously, avoiding GPU idle. Lastly, elastic straggling strategy batches different sets of trials, removing redundant model loading operations. These strategies enhancing overall system throughput and reduce our mix-man by 1.3 to 1.8 times. For more details on the data center characterization and workload profiling and other stuffs, we have profiling MOE models or on 1K GPUs and other statics and our full failure analysis. Please refer to our paper for more details. As a summary, we analyze large language model workloads and resource utilization in our data center Acme, revealing unique features and challenges of LLM development, such as resource efficiencies and failure impacts. We also uncover potential opportunities to optimize systems tailored for evaluation workloads. We believe that our lessons and insights have brought applicability and will benefit for the future research. Thank you.